Okay, here's the graph of the two functions over here to the right. And I've put on here the point of intersection is 4, 2. I'm not going to go into too much detail how I discovered that. You can try to use the substitution method or graph both functions on a graphing calculator and find the point of intersection that way. But here's kind of proof that the point 4, 2, 2 works for both of these relations. So 4 to the second, does that equal 2 to the fourth? Yeah, 16 equals 16. And does 2 equal the log of 4 base 2? Yes, because 2 times 2, or 2 squared, I should say, is 4. So 4, 2 indeed is the point of intersection. So to find the slopes of the tangent lines, like there's one and there's the other one, we need to find the derivatives of each of these and then substitute in 4 for x and 2 for y. So this first function, log of x base 2, is pretty straightforward standard derivative formula. To see why that works, or why you need ln of 2 in the denominator, if you use the change of base formula to write it this way, then the derivative becomes apparent. We have the numerical coefficient is 1 over ln of 2, and the derivative of the numerator is 1 over x. And that's why we get this formula for the derivative. And when x is 4, which is the only variable in the derivative definition, we get 1 over the ln of 16. So that's your exact answer there. It's a little harder to find the derivative of y with respect to x here. Start by taking the natural log of both sides. Excuse me. That allows us to bring these exponents down front, which I've done here. And now we're going to use implicit differentiation, and we have to use the product rule on each side. So it's the first function times the derivative of the second, plus the second function, which is ln of x, times the derivative of the first, which is y prime. And on the right side, similar technique, use the product rule. First times the derivative of the second, which is 1 over y, times y prime. We have to use the chain rule there because we're assuming y is some function of x. And then plus the second function times the derivative of the first. I could have shown a 1 out here to represent the derivative of the first. Now what we do is get the terms with y prime on one side of the equal sign and the other terms on the other side, and then factor out the y prime, which is what I've done up here. Divide both sides by this expression, and there's a formula for slopes of tangent lines to the graph of this relation. So if I want to find y prime of 4, 2, put 4 in for x, 2 in for y. That's a possible answer. If you don't like complex fractions, multiply numerator and denominator of the big fraction by 2. That'll get rid of that 1/2. And then if you want to, you can move these 2's up front. And you get log of 4 minus 1 divided by ln of 16 minus 4. Okay, and if I go to the second board, you can see some decimal approximations for these slopes. I have the terms in the numerator and denominator switched when I did the problem originally. But that's the slope of, well, I don't know which one that's the slope of, but, oh yeah, it's the the red slope right here, the red tangent line. And here's the equations of those tangent lines. Y minus 2 equals slope m sub 1 times the quantity x minus 4. And here's the slope of the black tangent line to the graph of y equals log of x base 2. Okay, there you go. Hope that helped. If you have any questions, post a comment.